Well, hello everyone, and in this series of videos I'm going to be going over the basic concepts of electronics. So we're going to be going through the beginner to advanced electronics. So in this section of the course we're going to be talking about electronic foundations. We're going to be using the art of electronics as a reference and mainly following that, but I will supplement some examples by taking references from electric circuits as well. I just found that the art of electronics did lack a little bit on certain examples. So let's get started. So in this part of the course we're going to be talking about voltage, current, and resistance, signals, capacitors and AC circuits, inductors and transformers, diodes and diode circuits, impedance and reactance, as well as other passive components. Voltage, current, and resistance. So, voltage and current sources. A voltage source is a device or component that provides a fixed or controlled potential difference between its terminals, regardless of the current drawn. It pushes electric charge through a circuit by maintaining a set voltage. It can be independent, example like a battery, or dependent/controlled, like this one. An ideal voltage source maintains constant voltage no matter the current drawn. It has zero internal resistance, whereas a real voltage source, like a battery, has some internal resistance, so voltage may drop under high load. So these are examples of voltage sources. This is usually a DC, an AC, another version of a DC one, and then a dependent or controlled voltage source. A current source is a device or component that delivers or maintains a constant current to a circuit, regardless of the voltage across it, within its operating limits. It pushes a fixed amount of electric charge per unit time. It can be independent or dependent, like this one here, and this is an independent. An ideal current source maintains constant current regardless of the load's resistance. It has infinite internal resistance. A real current source can only maintain the current within a certain voltage range before its output changes. Voltage and current. So voltage is the electric potential difference between 2 points in a circuit. It tells you how much potential energy per unit charge is available to move electrons from one point to another, much like the pressure that pushes water through a pipe. Voltage has a symbol V and is measured in volts. Electric current is the flow of electric charge through a conductor or circuit. It measures how many charges pass a point per unit time. Similar to the flow rate of water in a pipe, current has the symbol I and is measured in amps. So Kirchhoff's current law, or KCL for short, states that the total current entering a junction or node in an electric circuit is equal to the total current leaving that junction. Mathematically, the sum of the input current is equal to the sum of the output current. It's based on the principle of conservation of electric charge. Charge cannot accumulate at a node, so whatever current enters must leave. Next is Kirchhoff's voltage law, or KVL for short. The algebraic sum of all charges around any closed loop in a circuit is zero. Mathematically, the sum of the voltages is equal to zero. As you travel around a closed loop in a circuit, the total energy gained by charges from sources like batteries equals the total energy lost across resistors, capacitors, etc. This is a consequence of the conservation of energy. Electrical power is the rate at which electrical energy is transferred or converted in a circuit. It tells you how quickly electrical energy is being supplied by a source or used by a load. Power has the symbol P and is measured in watts. The formula is P is equal to VI. Power goes into heat, usually, or sometimes mechanical work like motors. It can be radiated as energy, such as lamps or transmitters, or stored energy, batteries, capacitors, and inductors. And this is just a figure that illustrates KCL and KVL. So you can see a node here. So the currents coming in, I1, I2, I3, is equal to the currents going out, I5 and I4. Similarly, Kirchhoff's voltage law, with all these voltages going in a loop, we have the sum of the voltages equal to 0. Example of using KCL. So in this circuit here, sum the currents at each node in the circuit shown in this figure. Note that there is no connection dot in the center of the diagram, where the 4 ohm branch crosses the branch containing the ideal current source, IA. So in this solution, we write these equations. So for node A, we see that I1 is leaving, and then I4 is leaving, I2 is coming in, and I5 is coming in. For node B, I2 is leaving, I3 is leaving, but I1 is coming in, IB is coming in, and then IA is coming in. For node C, we have IB coming out of node C, and then I3 going in, I4 going in, and then IC going in. And similarly for node D, which you can see here. Alright, for KVL, sum the voltage around each designated path in the circuit shown here. So for path A, which would be this. Alright, let's see. So for the direction of the current, we have negative because we're rising, so negative V1, and then we're following, so positive V2, positive V4, and then we're rising again, so negative VB, and then we're rising again, V3. For path B, we are rising, so negative VA, falling V3, and then falling V5, positive. For path C, we are, let's see, falling for VB, rising for V4, so negative, rising for VC, negative, so, and rising for V6, negative, and rising for V5, negative. And then finally for path D. Alright, so we have negative VA for rising, negative V1 for rising, positive V2 for falling, and negative VC for falling, a falling V7, and then a rising VD. Relationship between voltage and current. Resistors. A resistor is an electrical component that opposes the flow of electric current, converting some of the electrical energy into heat. The symbol for resistance is R and has the unit ohm. Ohm's law, which is very important, is V is equal to IR, or voltage is equal to the current times resistance. Resistors are used to control current in a circuit, divide voltage, protect components, and to convert electrical energy into heat. A resistor is made out of some conducting stuff, such as carbon, thin metal, or carbon film, or a wire of poor conductivity, with a wire or contacts at each end. The total resistance of resistors in series is R total equal to R1, R2, plus R3, etc. And the total resistance of the resistors in parallel is equal to 1 over R1, plus 1 over R2, plus 1 over R3, etc. Two resistors in parallel, R is equal to R1 over R1 plus R2, like this. Using Ohm's law, the power in a resistor is defined as P is equal to IV, which is equal to I squared R, which is equal to V squared over R. Example, you have a 5K resistor and a 10K resistor. What is their combined resistance in series and parallel? So in series, it would just be them added up together for 15,000. Then using the equation above, we get 3.33 kilo ohms. So, an example, applying Ohm's law and Kirchhoff's laws to find an unknown current. So, use Kirchhoff's laws and Ohm's law to find I naught in the circuit shown below. Test the solution for I naught by verifying that the total power generated equals the total power dissipated. So we begin by redrawing the circuit and assigning an unknown current to the 50 ohm resistor and unknown voltages across the 10 ohm and 50 ohm resistors, as shown in this circuit here. Because I naught also is the current in the 120 volt source, we have two unknown currents, and therefore must derive two simultaneous equations involving I naught and I1. We obtain one of the equations by applying Volchev's current law to either node B or C, summing the currents at node B and assigning a positive sign to the currents leaving the node. It gives I1 leaving, I naught going in, and 6 amps going in. We obtain the second equation from Kirchhoff's voltage law in combination with Ohm's law, noting from Ohm's law that V naught is 10 I naught and V1 is 50 I1. We sum the voltages around the closed paths to obtain negative 120 plus 10 I naught plus 50 I1 equal to 0. In writing this equation, we assigned a positive sign to voltage drops in the clockwise direction, solving these two equations for I naught and I1. So this would be a little bit more complicated for systems equations, but it is really just simple algebra to get I naught equal to negative 3 amps and I1 equal to 3 amps. B. The power dissipated in the 50 ohm resistor is equal to 3 squared times 50 for 450 watts. The power dissipated in the 10 ohm resistor is negative 3 squared times 10, which is equal to 90 watts. Power delivered to the 120 volt source is negative 120 I naught, which is negative 120 times negative 3 equal to 360 watts. Power delivered to the 6 amp source is negative V1 times 6, and V1 is equal to 150 volts. Therefore, the power delivered to the 6 amp source is negative 900 watts. The 6 amp source is delivering 900 watts, and the 120 volt source is absorbing 360. The total power absorbed is 360 plus 450 plus 90, which is equal to 900. Alright, voltage divider. A voltage divider is a simple circuit that uses two or more resistors in series and produces an output voltage that is a fraction of the input voltage. It works by dividing the total voltage in proportion to the resistances. If R1 and R2 are in series, and the input voltage Vin is applied across them, the voltage across R2 is Vout equal to Vin times R2 over R1 plus R2. Voltage dividers are used to scale down voltages for sensors, measurement circuits, or biasing transistors. They only work well when the load connected Vout to Vout draws a negligible amount of current. Additionally, I is equal to Vn over R1 plus R2. Example of a voltage divider. For this circuit, find the no load value of V naught in the circuit shown, and find V naught when RL is 150 kilo ohms. How much power is dissipated in the 25 kilo ohm resistor if the load terminals are accidentally short-circuited? What is the maximum power dissipated in the 75 kilo ohm resistor? So, we can use voltage division to calculate the voltage across the 70 kilo ohm resistor. So V naught over no load is equal to 75k over 75k plus 25k times 200, which gives us 150 volts. When we have a load resistance of 150 kilo ohms, then the voltage across V naught is the parallel combination of the 75 kilo ohm resistor and the 150 kilo ohm resistor. First, we calculate the equivalent resistance of the parallel combination. So 75 in parallel with 150 is equal to 50,000 ohms. Now we use voltage division to find V naught across this equivalent resistance, which is equal to 133.3 volts. If the load terminals are short circuit, the 75 kilo ohm resistor is effectively removed from the circuit, leaving only the voltage source and the 25 kilo ohm resistor. We can calculate the current using Ohm's law. So 200 over 25 gives us 8 milliamps. Now we can use the formula P is equal to I squared R to find the power dissipated in the 25 kilo ohm resistor. So 25,000 times 0.008 squared is equal to 1.6 watts. The power dissipated in the 75 kilo ohm resistor would be maximum at no load, since V0 is maximum in part A. We determined that the no load voltage is 150 volts, so we can use the formula P is equal to V squared over R to calculate the power, which would be 0.3 watts. Current divider. A current divider is a circuit, usually resistors in parallel, that divides an input current into two or more branch currents in inverse proportion to the branch resistances. The branch with a lower resistance gets more current. The branch with the higher resistance gets less current. For two resistors R1 and R2 in parallel with total current IS, I1 is equal to R2 over R1 plus R2. And I2 is equal to IS times R1 over R1 plus R2. So, just like before, find the power dissipated in the 6 ohm resistor shown here. First, we find the current in the resistor by simplifying the circuit with series parallel reductions. Thus, the circuit shown here reduces to the one shown here. We find the current I0 by using the formula for current division to get 8 amps. Note that I0 is the current in the 1.6 ohm resistor. We can now further divide I0 between the 6 ohm and 4 ohm resistors. The current in the 6 ohm resistor is 3.2 amps, and the power dissipated in the 6 ohm resistor is 61.44 watts. The Thavian equivalent circuit. A Thavian equivalent circuit is a simplified representation of a complex linear electrical network seen from two terminals that makes analysis easier. It replaces the original network with a single voltage source in series with a single resistor R Thavian. V Thavian is equal to the open circuit voltage measured at two terminals with low connected, and R Thavian is the resistance seen at terminals with all independent voltage sources replaced by short circuits and all independent current sources replaced by open circuits. The Thavian model makes it much easier to analyze how a load will behave when connected to a complex network. And these are the formulas for V Thavian and R Thavian. For example, in a voltage divider, the open circuit voltage is equal to Vn times R2 over R1 plus R2. And the short circuit current is I short circuit equal to Vn over R1. So the Thavian equivalent circuit is a voltage source. V Thavian equals Vn times R2 over R1 plus R2. In series with the resistor R Thavian equal to R1 times R2 over R1 plus R2. Example of finding the Thavian circuit. To find R Thavian in this circuit here, replace the 72 volt source with the short circuit. Note that the 5 ohm and 20 ohm resistors are in parallel with an equivalent resistance of 5 in parallel with 20 to give 4 ohms. The equivalent of 4 ohm resistance is in series with the 8 ohm resistor, or an equivalent resistance of 4 plus 8 equal to 12 ohms. Finally, the 12 ohm equivalent resistance is in parallel with the 12 ohm resistor. So R Thavian is equal to 12 in parallel with 12 equal to 6 ohms. Using node voltage analysis to find R Thavian, we begin by redrawing the circuit and labeling the node voltages V1 and V Thavian. The node voltage equations are V1 and V1 minus 72 over 5 plus V1 over 20 plus V1 minus V Thavian over 8. And then the other equation is V Thavian minus V1 over 8. And then plus V Thavian minus 72 over 12. Solving these systems of equations, we get V1 equal to 60 volts and V Thavian equal to 64.8 volts. Therefore, the Thavian equivalent circuit is 64.8 volts. Source in series with a 6 ohm resistor. Alright, diodes. A diode is an electronic component that allows current to flow in one direction only, while blocking it in the opposite direction under normal operating conditions. A diode is a triangle pointing in the direction of conventional current touching a vertical bar. A diode is forward biased when the anode is at a higher voltage than the cathode. The diode conducts after a certain threshold. That's 0.7 volts for silicon and about 0.3 volts for germanium. The diode is reverse biased when the cathode is at a higher voltage. The diode ideally blocks current except for a tiny leakage. The diode breaks down if the reverse voltage exceeds the diode's breakdown rating. It can conduct heavily, often damaging the diode, unless it's a Zener or special type. Diodes are commonly used for rectification, protecting circuits from reverse polarity, signal demodulation, and voltage regulation, such as Zener diodes. A Zener diode is a special type of diode to allow a current to flow not only in the forward direction, but also in the reverse direction. When the reverser voltage reaches a specific value called the Zener breakdown voltage, it looks similar to a diode but with the bent edges at the bar. The Zener voltage is the fixed voltage at which the diode conducts in reverse. In the reverse breakdown region, the voltage across the diode stays nearly constant, even if the current changes, which makes it useful as a voltage regulator, which is what you'll see in a typical application. Typical Zener voltage ranges from a few volts to tens of volts. They are mainly used for voltage regulation, as a reference voltage in circuits, and overvoltage protection. For example, a 5.1 Zener diode will start conducting in reverse when the voltage across it reaches 5.1 volts, clipping the voltage at that level. Signals. Sinusoidal signals. A sinusoidal signal is a type of continuous waveform that varies with time following a sine or cosine mathematical function. It is one of the most fundamental signals in electrical engineering and physics and is defined by the equation x of t is equal to a sine omega t plus phi, where a is the amplitude, omega or 2 pi f is the angular frequency in radians per second, f is frequency, phi is the phase angle, which is radians or degrees, and t is time. Decibels. A decibel, or dB, is a logarithmic unit used to express the ratio between two quantities. It is most commonly used for power or voltage. It is widely used in electronics, acoustics, and signal processing because it can represent very large or small ratios in a compact way. So LdB is equal to 10 log 10 of P over P reference, where P is the measured power, and P is the reference power, and LdB is the level in decibels. For voltage and current, since power is proportional to V squared or I squared, level dB is equal to 20 log 10 of V over V reference, or for log dB is equal to 20 log 10 of I over I ref. In the context of digital filters, the gain or amplitude response is expressed in decibels. When the decibels is positive, the gain is called amplification. When the decibels is negative, the gain is called attenuation. A negative 3 decibel point means the output power has dropped to half of the input power. In terms of magnitude, it means the output is at about 70.7% of input. In the filter design, the negative 3 dB frequency is called the cutoff frequency or half power point. It is the boundary where the filter starts to significantly attenuate the signal. A positive 3 dB gain means the output power is double compared to the input power. In terms of magnitude, it's about 1.414 times the input amplitude. In digital filters, this may indicate resonance or an amplification band. A low-pass filter might pass low frequencies unchanged. Then at the cutoff frequency, the response is down -3 dB, and higher frequencies are attenuated further. A bandpass filter might have a peak gain of 3 dB at the center frequency, meaning it slightly boosts signals there while attenuating others. So, the other kinds of signals. So we have a voltage ramp waveform, a ramp with a limit, a sawtooth wave, a triangle wave, noise, square wave, positive and negative pulses of both polarities, step and spike signals. Logic levels. Logic levels are the specific voltage ranges in a digital circuit that represent the two binary states, logic 0 or low, and logic 1 high. An example would be a transistor-transistor logic. So logic 0 would be 0 volts to about 0.8 volts, and logic high would be about 2 volts to 5 volts. Between 0.8 and 2 is undefined, so signals there are not guaranteed to be read correctly. Why voltage ranges and not exact numbers? Real circuits have noise, voltage drops, and variations in components. By allowing margin or a noise margin, digital systems stay reliable. Signal sources. A signal generator is an electronic device that produces repeating or non-repeating waveforms. It is used to provide test signals for analyzing and troubleshooting circuits. Common outputs include sine waves, square waves, or simple periodic waves. They are used for testing amplifiers, communication circuits, and measuring the frequency response of circuits, which we'll get into more later. A pulse generator is a specialized signal source that produces pulses, short-duration signals with defined amplitude, duration, and repetition rate. It usually produces square or rectangular pulses. The control parameters include the pulse width, repetition frequency, rise and fall time, and amplitude. It is used for clock signals in digital circuits, trigger signals in oscilloscopes, timing and synchronization applications. A function generator is a versatile signal source capable of producing multiple standard waveforms. Common outputs include the sine wave, square wave, triangle wave, sawtooth wave, and pulse range. It features an adjustable frequency, amplitude, offset, and sometimes modulation. It is used for testing filters, driving digital circuits, and general purpose testing in labs. Capacitors in AC circuits. Capacitors. A capacitor is a two-terminal device that stores electrical energy in an electric field. They are made up of two conductive plates separated by an insulating material or dielectric. When a voltage is applied across the plates, opposite charges accumulate on each plate, creating an electric field. Capacitance C, measured in farads F, is the ability to store charge per unit voltage. C is equal to Q over V, where C is capacitance, Q is the stored charge, and V is the voltage across the capacitor. The energy stored is E equal to 1/2 CV squared. For DC, after the capacitor charge is charged, it looks like an open circuit. For AC, the capacitor allows alternating current to pass. The impedance or resistance decreases with frequency. Capacitors are used for energy storage, filtering, coupling/decoupling signals in amplifiers, and in timing circuits. Capacitor types include ceramic, electrolytic, tantalum, film, supercapacitors, and variable. Capacitors in series versus parallel. When capacitors are in parallel or side by side, their capacitances add up directly. So the equivalent capacitance is equal to C1 plus C2 plus C3, etc. The plate area effectively increases, like making one big capacitor. As a result, there is a higher total capacitance with the same voltage across the capacitor. When capacitors are connected in series, the reciprocal capacitance adds up, as you can see here. The distance between the plates effectively increases, reducing capacitance. which means the total capacitance is smaller than the smallest capacitor in series. RC circuits, voltage and current versus time. An RC circuit is when a resistor and capacitor are connected in series or in parallel. Their key behavior comes from the time constant tau equal to RC, where tau tells us how quickly the capacitor charges or discharges. When a voltage source across the Vs is applied to an iron-charged capacitor through a resistor, the voltage across the capacitor increases exponentially, and the current through the capacitor decreases exponentially. So Vc of t is equal to Vs times 1 minus e to the negative t over Rc, and I of t is equal to Vs over R times e to the negative t over Rc. At t0, the capacitor behaves like a short circuit, so max current flows. As t approaches infinity, the capacitor is fully charged, so it acts like an open circuit, and the current is equal to 0. If the capacitor is initially charged to the initial voltage, and then allowed to discharge through resistor R, then the voltage across the capacitor decreases exponentially, and the current also decreases exponentially, as given by these equations. At t is equal to 0, the current is maximum, and at t goes to infinity, the capacitor is fully discharged and the voltage and current is 0. The time constant, tau, tells us how fast the response is. After 1 tau, the capacitor charges to 63% of the supply voltage. After 5 tau, charging or discharging is essentially complete. Example: determining the current, voltage, power, and energy for a capacitor. A voltage pulse described by the following equations is impressed across the terminals of a 0.5 microfarad capacitor. Derive the equations for the capacitor current, power, and energy. Sketch the voltage, current, power, and energy as functions of time. Specify the interval of time when energy is being stored in the capacitor. Specify the interval of time when energy is being delivered by the capacitor, and evaluate these integrals. So, with the current given by this equation here, we just take the derivative of this and multiply it by the capacitance, and we get this. The expression for power is derived by P is equal to VI, so we just multiply the voltage here by the current in any given sense of time. The energy is directly follows from this equation, 1/2 CV squared. So we get the energy here. So in this we get the graphs for the voltage and current and power and energy. RC differentiator circuits. An RC differentiator is built with a capacitor in series with the input signal and a resistor to ground. The current capacitor current is proportional to the rate of change of input voltage, IC equal to C dVin over dt. The same current flows through the capacitor V out is equal to ICR, which is equal to RC dVn over dt. For example, for a DC input of constant voltage, the derivative would equal to 0. Therefore, the output is 0. For a square wave input, the output is a sharp pulse, since the derivative of a step is an impulse. For a triangle wave input, the output is a rectangular wave, since the input would show no rate of change. Sine wave input, if Vn is equal to Vm sine omega t, then V out would be omega Rc Vm cos omega t, which is a 90-degree phase shift. RC integrator circuits. An RC integrator circuit is built with a resistor in series with the input signal and a capacitor to ground. From the capacitor voltage current relation, IC equal to d Vc over dt, but the current comes from the resistor IR equal to Vn minus Vc over R. Since IR is equal to ICVN over R, which is approximately equal to C times the derivative of V out, rearranging for V out, which is when it is much, much less than V in, V out is approximately equal to 1 over C times the integral of the input voltage with respect to time. For square wave input, the output is a triangle wave. For sine wave input, the output is a cosine wave, shifted by 90 degrees. For step input, the output is a ramp. For DC input, the output is a linear ramp until the capacitor saturates. For RC integrators only work well when the input signal's period is much smaller than RC. For precision, active RC integrators using op-amps are used. In summary, the RC integrator uses the resistor first and then the capacitor. The output is the integral of the input scaled by 1 over RC. The RC integrator converts square waves into triangle waves, sine waves, which are phase-shifted sine waves, and steps into ramps. Inductors and transformers. Inductors. An inductor is a passive electrical component that stores energy in the form of a magnetic field. When current flows through it, it usually consists of a coil of wire around a core. The inductance L is the ability of an inductor to oppose changes in current and is measured in henries. The voltage-current relationship VL is equal to L times the derivative of the input current. The energy storage is equal to E equal to 1/2 L times I squared. Voltage across an inductor is proportional to the rate of change of current. Current through an ideal conductor cannot change instantly, unlike capacitors where the voltage cannot change instantly. Energy stored in the magnetic field depends on current. In a DC steady state, the circuit behaves like a short circuit, just a wire. AC circuits, they oppose current flow with an inductive reactance. Applications include chokes, transformers, energy storage, radio tuning circuits, and inductive sensors and motors. Example: determining the voltage given the current at the terminals of an inductor. The independent current source in the circuit shown below generates 0 current for t less than 0, and a pulse of 10 times t to the e to the negative 5t amps for t greater than 0. So we sketch the waveform. At what instant of time is the current maximum? Express the voltage across the terminals of the 100 millihenry inductor as a function of time. So, this figure shows the current waveform, B. So, the derivative of the current is equal to 10 times negative 5 times t e to the negative 5t plus 5 to the negative 5t equal to 10 e to the negative 5t. C. For the voltage is equal to L times the derivative of the current, which would be e to the negative 5t times 1 minus 5t volts. This is the voltage waveform. Transformers. A transformer is an electrical device that uses the principle of electromagnetic induction to transfer electrical energy between two or more circuits, usually with different voltage and current levels, but the same frequency. It consists of 2 or more coils of wire called the primary winding or secondary winding around a magnetic core. An AC voltage applied to the primary coil produces the changing magnetic flux in the core. This flux induces a voltage in the secondary coil. The ratio of voltages depends on the turns ratio of the windings. Power is also conserved. So it is given by these equations, where V secondary and V primary are the secondary and primary voltages. There are 3 types of transformers: a step-up transformer, a step-down transformer, and an isolation transformer. Transformers are used in power transmission, power supplies, and impedance matching and communication systems, and isolation for safety in sensitive circuits. Diodes and diode circuits. Diodes. A diode, as discussed before, is a two-terminal semiconductor, the device that allows current to flow in only one direction and blocks it in the opposite direction under normal operation. It's the simplest semiconductor device used by joining p-type and n-type materials, thereby forming a p-n junction. Diodes have an anode and a cathode. They look like a triangle and against a vertical bar. Diodes have 3 operation modes and forward bias. The anode is connected to the positive and the cathode to the negative. The diode conducts after a threshold voltage is reached. The diode acts like a closed switch above the threshold. In reverse bias, the anode is connected to negative and the cathode is connected to positive. The diode ideally blocks current. Only a tiny leakage current flows. The diode goes into the breakdown region. If reverse voltage exceeds the breakdown rating, the diode will conduct heavily. This normally changes the diode and damages the diode unless it's a Zener diode. Diodes are normally used as for rectifiers in clamping and clipping, voltage regulation, switching, and protection. Rectification. Rectification is the process of converting an alternating current into a direct current signal. This is achieved using diodes, since they allow current to flow only in one direction. Most electrical power is supplied as AC, but many devices require DC. Rectifiers are used inside power supplies to form this conversion. There are 3 types of rectifiers. A half-wave rectifier uses only one diode and passes only the positive half cycles of AC and outputs a pulsating DC with large gaps. It is simple but inefficient. A full-wave rectifier uses 2 diodes and a center tap transformer, and both halves of the AC are rectified, producing pulsating DC. It has better efficiency than the half-wave. A full-wave bridge rectifier uses 4 diodes in a bridge arrangement. No center tap is required, and both halves of the AC are rectified, thereby continuous pulsating DC. They are most common in power supplies. To smooth the output, we add a capacitor. For a half-wave rectifier, the average DC voltage is equal to V magnitude over pi, and for a full-wave rectifier, the average DC voltage is equal to 2 times V magnitude over pi. Power supply filtering. Filtering is the process of reducing ripples or fluctuations in a rectified DC signal to produce smoother, more stable DC output. After rectification, the output is pulsating. Filter circuits, typically capacitors, inductors, or both, smooth this into a usable DC. A capacitor filter is when a large electrolytic capacitor is connected across the rectifier output. The capacitor charges during voltage peaks and discharges when voltage drops. This fills in the gaps between pulses, thereby reducing the ripple. This filter works best for light to moderate loads. An inductor filter is when an inductor is placed in series with the rectifier output. Inductors resist changes in current, so they smooth the small pulsating DC by averaging the current flow. This filter works well for heavy loads, but inductors can be bulky. An inductor capacity filter is the combination of a series inductor and shunt capacitor. An inductor smooths current and the capacitor smooths voltage. This filter has much better ripple reduction than either one alone. A pi filter looks like the Greek letter pi, with a capacitor, inductor, and capacitor. The first capacitor reduces high-frequency ripple. The inductor smooths current. The sector inductor reduces residual ripple. It is a very effective filter and is widely used in regulated power supplies. The goal is to reduce the ripple voltage, defined as the variation of DC voltage after filtering. For a capacitor filter on a full-wave rectifier, VR is equal to I load over 2 frequency C. And these are the examples of the power supply filters. So you have the capacitor, inductor, inductor capacitor, and then the pi. A voltage regulator is an electronic circuit or device that maintains a constant DC output voltage, even if the input voltage varies and/or the load current changes. This ensures electronic devices receive a stable supply voltage. Since the rectifier and filter output of a voltage source is still not perfectly steady, regulators are used to maintain a steady voltage like 5 or 3.3 volts. Linear regulators are simple and lower noise. They work like an automatic variable resistor that drops extra voltage. Examples include the 78XX series of chips. They are considered to be cheap, low noise, and easy to find. However, they are inefficient at high currents. A Zener diode rectifier is when a Zener diode in reverse breakdown clamps voltage to a set level. It is used for simple and low current regulation. Switching regulators use high-frequency transistors and inductors/capacitors to efficiently step voltage up, down, or invert it. They include the buck step down, boost step up, and buck boost inverts or regulates up-down regulators. They are very efficient and can output higher or lower voltage than input. However, they are more complex and produce noise. Inductive load protection. An inductive load is any device that contains a coil of wire and therefore stores energy in a magnetic field when current flows. Examples include relays, motors, solenoids, and transformers. The problem with inductive loads is inductors resist sudden change in current. When you turn off current to an inductor, the magnetic field collapses. The collapsing field induces a large voltage spike. The spike can be much higher than the supply voltage and can damage transistors, switch, or ICs controlling the load. This is often called the EMF or electromagnetic force. To protect currents from this high voltage spike, we use a diode across the inductive load. The diode is replaced in reverse bias relative to the supply voltage. During normal operation, the diode does nothing. When the current is suddenly interrupted, the inductor's collapsing field drives current in the opposite direction. The diode provides a safe path for this current, allowing it to circulate until the energy is dissipated. This clamps the voltage spike to about 0.7 volts, protecting the switch or transistor. Other protection methods include snubber circuits for AC inductive loads, TVS diodes for fast clamping, and MOVs for surge protection. Impedance and reactance. Impedance and reactance overview. In AC circuits, capacitors and inductors oppose current flow, but in a frequency-dependent way. This opposition without energy loss, just phase shift, is called reactance. Inductive reactance is equal to 2 pi FL. It increases with frequency. Inductors resist high-frequency AC more strongly. Capacitive reactance is XC equal to 1 over 2 pi FC. It decreases with frequency. Capacitors resist low-frequency AC more strongly. Impedance Z is the total opposition to AC, combining resistance, the real part, and reactance, the imaginary part, where Z is equal to R plus JX, where J is equal to the square root of -1. If X is equal to XL minus XC greater than 0, then the circuit is inductive, i.e. the current lags voltage. If X is less than 0, the current is capacitive, current leads voltage. The magnitude of impedance is Z equal to R, the square root of R squared plus X squared. The frequency analysis of reactive circuits. Reactive components, like capacitors and inductors, don't behave like fixed resistors. Their opposition to current depends on frequency. An inductor blocks high frequencies and passes low frequencies. A capacitor blocks low frequencies and passes high frequencies. A low-pass RC filter is when a capacitor shunts high frequencies signals to ground. Low frequencies pass through and high frequencies are attenuated. The cutoff frequency is 1 over 2 pi RC. A high-pass RC filter is when a capacitor and resistor are in series. High frequencies pass through, and low frequencies are attenuated. A low-pass RL filter is when an inductor and resistor are in series, and a high-pass RL filter is when a resistor and inductor are in series. When resistors, capacitors, and inductors combine in RLC circuits or resonance circuits, at resonance, when XL is equal to XC, the impedance is purely resistive. For series resonance, there is minimum impedance, which means there is a maximum current. For parallel resonance, there is a maximum impedance, which means the circuit will block the resonant frequency. The resonant frequency for RLC circuits is Fc equal to 1 over 2 pi the square root of Lc. Voltages and currents as complex numbers. In AC circuits, voltages and currents are sinusoids. V of t is equal to V magnitude sine of omega t plus phi v. And I of t is equal to I magnitude and sine of omega t plus phi I, where V, M, and Im are magnitudes, omega is the angular frequency, and phi v and I are phase angles. Handling sine waves with phase shifts gets messy in the time domain, so we use phasors. A sinusoid can be written as a rotating complex vector. For example, V vector is equal to V magnitude e to the j phi v. I phasor is equal to I magnitude e to the j phi I. And j is equal to the square root of -1. So for example, for V of t equal to 10 sine omega t plus 30 degrees, we get V, a voltage of 10 to the angle 30 degrees. For resistors, the voltage and current are in phase. For an inductor, the voltage leads the current by 90 degrees, and for a capacitor, the voltage lags the current by 90 degrees. Power and reactive circuits. For instantaneous power in AC circuits, PT equal to Vt times It. If the voltage and current are not in phase, the power oscillates between positive, delivered to load, and negative, returned to source. The average real power, P, is the true power dissipated as heat, light, or mechanical work. P is equal to V RMS times I RMS cosine phi, where phi is the phase difference between voltage and current. The reactive power, Q, is the power alternatively stored and released by inductors and capacitors. Q is equal to V RMS I RMS sine phi, where positive Q is inductor-dominated lagging power factor, and a negative Q is capacitor-dominated leading power factor. The apparent power, S, is the total power flow in the circuit, the combination of real and reactive. The units are volt amps. It is expressed as a complex number, S equal to P plus JQ. The power factor is equal to the cosine of phi, which is equal to power P over S. Finally, we go into other passive components. Switches. There are manual switches and automatic switches. A single pole, single throw is the simplest on-off switch and controls one circuit. Double pole, single throw is when two inputs controlled together, each with one path. Double pole, double throw is when two inputs each can connect to two outputs. Double pole, double throw switches are used in motor reversing and complex control. Switches based on actuation include the toggle switch, push button switch, rotary switch, rocker switch, slide switch, and joystick switch. Special types of switches include the relay, a contactor, a limit switch, a reed switch, a mercury switch, dip switches, membrane switches, and touch switches. Automatic protection switches include circuit breakers, thermal switches, and pressure switches. Connectors. Power connectors are designed to safely carry electrical power. They include burial connectors such as DC jacks or plugs. They are common in wall adapters for electronics, Molas connectors, Anderson power pole connectors, and banana plugs and jacks. Signal/data connectors carry communication signals. They include USB, HDMI, Ethernet, audio jacks, DisplayPort, and Lightning. RF or radio frequency connectors are specialized for high frequency signals. They include BNC, SMA, N-type, and F-type. Board-to-board and wire-to-board connectors are used inside devices to connect circuit boards and wires. They include pin headers, male-female, Berg IDC ribbon cable connectors, JST connectors, card edge connectors, and zero insertion force / ZIF connectors. Specialized connectors include DIN, D-sub, magnetic connectors, waterproof / shield connectors, and coaxial power connectors. Industrial and high power connectors include XLR, spoken, camlock, terminal blocks, and heavy-duty circular connectors. Indicators. Visual indicators use light or display switches to show circuit status. Lamps and bulbs include incandescent lamps, neon lamps, LEDs, LED displays. Another includes 7-segment displays, 14-16 segment displays, and dot matrix displays. LCD indicators are low power and are used in calculators, watches, and multimeters. They can be alphanumeric or symbolic. OLED indicators are brighter than LEDs and can show text and graphics. They are used in wearables, small control panels. Bar graph indicators are a series of LEDs arranged in a line. Audible indicators give sound feedback instead of light. Think of buzzers, and speakers and tone generators. Electromechanical indicators physically move parts to indicate status. These include analog meters and flip-dot displays. Specialized indicators include status LEDs and connectors, pilot lights, and smart indicators. Variable components. Variable resistors are resistors whose resistance can be adjusted. They include potentiometers, rheostats, digital potentiometers, photoresistors, and thermistors. Variable capacitors are capacitors whereby the capacitance can be tuned. They include air dielectric variable capacitors, trimmer capacitors, and variactor varicap diodes. Variable inductors are inductors where inductance is adjusted. Adjustable core inductors and saturable reactors. Other variable components include varistors, MEMS variable devices, and FETs/MOSFETs. Alright, that concludes this video. Thank you all for watching. As always, the notes will be in the description below. And everyone have a nice day.